Good morning, everyone. I'm Rebecca Wright, Chair of Computer Science at Barnard. We are happy to have Samantha Chen with us today for our computer science seminar. She is a PhD student at the University of California, San Diego, and is advised by Yusu Wang. Their research is in the intersection of machine learning and computational geometry, and they've worked on problems related to graph neural networks, geometric deep learning, geometric algorithms, and optimal transport. And Samantha did their undergraduate degree in mathematics and computer science at Carleton College in Northfield. And Sam will be talking to us today about their work on algorithmic problems and neural networks. The floor is yours.
Okay, great. Okay, so hi everyone. Yeah, as Rebecca said, I'm Sam. I'm very pleased to be here today talking to you all about my research. Okay, so before I get into it, so I guess oh, sorry. Okay, so I guess in traditional machine learning, you might be used to really thinking about mapping one single input vector to some output label, right? But these days, the data that we're working with is often more complex than just some vector in Euclidean space. So for instance, it's really common to it's really common to have point cloud or point set structured data that's taken from scans of 3D objects or from LiDAR or satellite scans. And then we also have data where we want to be able to capture relationships between objects, right? So in which case, we can model it as a graph. So you can think of social media networks or molecular graphs, or also graphs which represent some neuron structure. So in each of these scenarios, we want to take advantage of advancements in machine learning to solve problems on this kind of geometric data. And indeed, there are neural networks which are designed to work on point clouds and graphs. And broadly, we call this sort of machine learning techniques or neural networks that are used to operate on this sort of geometric data as geometric deep learning techniques. And later in my talk, I'll highlight two types of neural networks which operate on this kind of data. Okay. Oops. So, but one issue that we have to keep in mind when working with geometric deep learning in particular is how it generalizes out of distribution.
And you might want to stand on the side, yeah, because we can't see.
Oh, I'm so sorry. Okay.
Maybe if you're on that angle, then a lot of
Okay.
Sorry, thank you.
I'm sorry. Okay.
It's so much nicer.
Sorry. Okay. So one issue that is particularly salient for this geometric deep learning techniques is this out of distribution generalization problem. So in general, out of distribution generalization refers to you might encounter test data that comes from very different or looks very different from your training data, right? And you still want your neural network to act robustly on this data, or you at least want to know okay, where is my neural network going to fail? Where is my machine learning technique going to fail? When we're working with data like point clouds and graphs, the test objects and test problems might not just look very different from what you encounter at training time. It could also be much larger than what you encounter at training time, right? So you can imagine a situation where you're training on very small graphs, but you still want whatever network you've trained to work well on large graphs. So this is the issue that I'm particularly interested in. When can these geometric deep learning techniques approximate solutions that can generalize to larger instances of the problem, or larger instances of graphs and point clouds? Okay. So there is a lot of previous work in this area as well. So for traditional feed forward neural networks, people have found that when you go way out of the training distribution, whatever function that you learn is going to just converge to some piecewise linear function. For the more complex geometric deep learning architectures, a lot of the results require some conditions on the test and train distributions. So it'll be things like okay, my graph neural network or whatever neural network I've trained on my graph structured data is going to generalize to larger graphs, but only if my test graph is coming from the same like maybe underlying manifold or graphon as my training graphs. Okay.
I'm a little confused about the first one because aren't feed-forward neural networks with brand new activations already piecewise linear?
Yeah, but I guess like you can get them to sort of overfit, I guess, like these sort of, you know, like this sort of or wavy function or yeah, but like when you go way out of the training distribution, like they'll just be linear. Okay. Okay, yeah. Yeah, just a picture will illustrate it. Yeah. Okay. So another way that people think about like solving this out of distribution generalization problem, and indeed the way that I'm going to focus on for the rest of this talk is through this paradigm called algorithmic alignment. So let me give you like a small example. Let's say you have some input value and some desired output label. Okay, you know that there's like some iterative algorithm that where one can map this input to my desired output. And of course, we can just ask a neural network to just map, you know, from my input to output. But intuitively, this sort of requires us to kind of learn this whole for loop, right? Another idea is to maybe I can just ask maybe I can just ask my network to just learn this inner iterative body, okay? And then in that way, it sort of learns some, you know, general submodule or general procedure for mapping from my input value to my output value, okay? And then, so this is kind of the idea of algorithmic alignment in general. So we want to decompose our neural network to follow some algorithmic structure, or we want to bias it towards some algorithmic structure in hopes that it will learn like a procedure that can generalize across different sizes or across different problem instances. People have shown that like if you do this, you can get some better sample complexity, or like basically you require less training data to reach like the same accuracy on your test data. And then also in terms of like when you actually ask the neural network to learn some algorithmic procedure, people have found that it actually like empirically gives you better results and also like allows you to transfer a trained network between doing like different tasks. Okay. Okay, so let me just be very clear about the setting. So we're trying to focus on like asking like when can a neural network learn to execute classical algorithms or to approximate solutions to like algorithmic tasks, like things like maybe shortest path on graphs or the minimum spanning tree, or maybe convex holes for a set of points. Okay, so you may be asking yourself at this point, why? Like, why would I want to do this? You know, why don't we have very nice algorithms for these. Like, why don't we just let the algorithm be the algorithm? Why ask a neural network to do all this? Well, in general, like these algorithmic tests are very useful test beds for understanding like the limitations of our techniques and the limitations of our methods. And then for some like hard problems, maybe we can even learn like faster solutions. And finally, like for each algorithm, right, it needs to have an explicit goal. We need to know like what we want, but sometimes you only have labeled data, right? So maybe we can get around this by using a neural network to use some procedure to like achieve some implicit goal, okay? So like this algorithmic alignment setting is just very useful in understanding like the limitation of your neural network, and especially in their ability to learn some generalizable procedure or submodule, okay? And you can imagine if a neural network can learn to execute an algorithm, it can very naturally generalize out of distribution, okay? Okay, let me just give you a roadmap for where like the rest of my talk will go. So first I'll talk about like when we can guarantee that an algorithm will be learned. And we do this in the context of graph neural networks in shortest paths. And then the second part is a little more empirical, and we look at like how to design neural networks that can solve like hard shape fitting problems using like these algorithmic alignment ideas. Okay.
Just ask about what you said before. So your out of distribution thing is for any arbitrary distributions that follow this algorithmic structure, right?
I guess like we're talking about any, I guess, okay, for like if we take the example of graphs, we're talking about like any size or type of graph, like your neural network is going to work, like or is going to give you a good result on this graph, or going to give you like a reasonable result. Yeah.
In your very simple example, you had an if condition, then do some iterative thing.
Yeah.
So you would work in any instance that has this structure, but possibly with different if conditions, but it will have to have the same iterative thing. Otherwise, why does it help you to learn the iterative thing?
Yeah, exactly. So sorry, yeah, we're working on like some task, some specific task. Okay, but like you want to be able to learn how to do this task on any instance of your problem. Does that make sense?
I guess you're learning a specific algorithmic alignment is a specific structure, and you want to learn on any task that fits the structure, right? You're saying it will help me to learn other distributions that are not within this
Yes,
structure.
yeah.
Okay.
Okay.
Yeah.
Okay, so let's talk about this first part first. And let me also give you a brief introduction to graph neural networks and learning on graphs, in case you haven't seen it before. Okay, I guess before we talk about graphs, let's talk about images. That's maybe something that more people are familiar with in this room. So if I ask you to like create a classifier to distinguish between a dog and a cat, probably you will tell me, okay, maybe you should use a convolutional neural network, right? That's sort of a canonical solution. I guess maybe now you will say a transformer, but previously you might have said a convolutional neural network. Okay, so for a convolutional neural network, you kind of learn to compute a new feature per pixel by aggregating over like neighboring pixels, right? Using your convolutional kernel, right? So we want to extend this paradigm then to graphs, like so the idea is like given a graph, we want to compute a new feature per node by aggregating over all neighboring features. Okay, it's a little different from the image case because now like graphs can have an arbitrary number of neighbors. It's not so structured as an image. Okay, so let me start with a labeled graph here, and let's say that I want to compute a feature for like node 5. So what I will do is I will just aggregate maybe the features from my neighboring nodes here, 4, 2, and 1, okay? And then after aggregating, I'm going to update my node feature based on like the neighboring node features, okay? And indeed, this encompasses like this sort of message passing or like neighborhood aggregation paradigm encompasses a whole class of neural networks that we call message passing GNNs. Yeah, usually when people refer to GNNs, this is like what they're referring to, although there are other things that you can use to learn on graphs. Okay, so let me just be also like very formal about the input here for our neural network. So you have a graph with vertices and edges, okay? And then you also have a set of initial node features, okay, on your vertices. And you may also have a set of edge features, okay? Although this isn't always the case. And then at each layer, I'm going to aggregate all my neighboring node features and also my neighboring edge features, and then compute and then update my like node feature in question according to what I've aggregated, okay? Here's an illustration. Hopefully this makes it a little clear. But practically, you can implement these many ways, okay? So these are 3 very popular GNN architectures that one can use. And I think there's like some subtle ways in which they're different, but the main difference between them is their aggregation function. Okay, so like this GCN network will use like a mean aggregator. This GIN is going to use some aggregation, and this MPNN max is going to use this max aggregation. And this aggregation function is quite important because practically the performance of the GNN will really change based on the aggregation. Okay, so I like won't get into the theory, but basically like these aggregation functions will control like how large of a function class your GNNs can represent. Okay, so what does this all have to do? Like, how is this connected with algorithmic alignment? Why are people so interested in GNNs and algorithmic alignment? Well, you can observe that at each layer, the graph neural network looks very similar to like dynamic programming, or in particular, people notice this for Bellman-Ford, okay? So in like the Bellman-Ford shortest path algorithm, you update your distance to source by like looking at all your neighbors along with the neighboring edge features. And then in the GNN, you sort of do the update a very similar way. Like you look at all the neighboring features and then you update based on your neighbors, okay? And I guess like indeed this GNN update, people observe that it sort of looks very similar to like a dynamic programming update in general, okay? There's been lots of like empirical work on this, trying to see is using a GNN to like learn solutions to dynamic programming problems is actually better? And people have found that like empirically, okay, yeah, it seems that GNNs can really get some better results when we ask them to learn dynamic programming problems. But in our work, in this following work with my wonderful collaborators, Riley, Sandra, and of course my advisor, Yusu, we showed that a graph neural network, which is specifically aligned to Bellman-Ford, will actually learn to implement the algorithm as long as it reaches some low loss, okay? And this means that like the GNN will actually generalize out of distribution because it's actually really learned to implement the algorithm. Okay. Okay, so let me give you like a quick reminder, and I guess this will also be relevant because it describes like the sort of input to the structure of the input to the network, okay? So this Bellman-Ford shortest path algorithm like computes the shortest path to the source. We start with a weighted graph and a specific source node S. And then initially we set the distance from source to itself to be 0 and for everything else to be infinity, right? And then at each iteration of Bellman-Ford, we update the current distance to source by just looking over all the distance to source of my neighbors and then adding the edge weight from the neighbor, okay? So for example, at step 0, like we start with the source node at 0 here, this green node. And then at step 1, we just update the neighbors of the source node, okay? Okay, so the model that we'll consider looks like this. We sort of want to explicitly align it to Bellman-Ford, so we'll use like a min aggregation function here, okay? Here's a picture also. So we're going to argue that this neural network with this structure that's explicitly aligned to Bellman-Ford through this min aggregator will actually learn to implement like one step of the algorithm or multiple steps of the algorithm, depending on how deep your GNN is. Okay, so let me give you some intuition using like a very small version of the model or a very small simple version of the model. Okay, so let's say that we have some graph G and then we initialize it just the same as how we like initialize this Bellman-Ford algorithm, okay? And then we update our node feature for like a single layer as follows here. So here I've just unrolled the computation of like the network. So like this W1 represents like the weights of that inner aggregation multi-layer perceptron. And then this W2 is like the weights of the outer one, okay? But because I want to keep it small, I'm just going to map like at the inner aggregation function, the output dimension will be 1. And then obviously for the update, it's like a mapping from a scalar to a scalar, okay? So to be clear, this W1 is an R2, and then the rest of the parameters here are scalars. So really very small model. Okay, there's like only 6 parameters. Okay. So if you look closely at this model, you may notice like if I set this W1 to just 1, 1, and then like this W2 to 1, and then the bias parameters to 0, then the output of my neural network will be exactly 1 step of Bellman-Ford. Okay? And actually, like, you don't need exactly these parameters. This will be true as long as like you have that this W2 times W1 is going to be 1, 1 here. Okay? And then all the parameters are non-negative. So it turns out that like if you train on the following small set of graphs, so like this single edge graph and this like 2-edge path, and if you reach like a low loss on this small set of graphs, then actually the parameters will exactly implement Bellman-Ford. The parameters will exactly like look like this, like what I said before. And then also, if you try to like actually do this training and actually go through and like train this network, this small network, you can see that through like by a gradient descent, your network will exactly reach those parameters that implement Bellman-Ford. Okay? Okay. So this analysis can also be extended to like wider and deeper GNNs of this following form too. The only thing that you need to add on is instead of just minimizing some mean squared error between like the single source shortest path distance at like some particular step, you have to add on also a sparsity regularization term. Okay? And then if your model like minimizes this particular loss function over a small set of graphs, then like we show that it will also exactly implement the Bellman-Ford algorithm and therefore like work also like be able to compute some k-step shortest path on arbitrary graphs. Okay. Okay, any questions at this stage? Yeah.
Yeah, just to make sure. Like when you say it implements Bellman-Ford, you mean like the weights in it, once you give it a new instance of a graph, will compute the Bellman-Ford path on.
Yes, yeah, exactly. Yeah. So the weights are exactly those where like it just matches up. Yeah, exactly. Yeah. Okay. Okay, so I guess there's like one thing missing here is like, how do we know this actually is going to work in practice? I mean, this sparsity regularization term, it's not differentiable. So we actually also like we tried to see, okay, what is this going to actually happen if I train a GNN? Okay. And it turns out that if you like use L1 regularization as a proxy for this like sparsity regularized this L0 regularization term, you actually get that, okay, so first, like, the network will minimize that, this, like, theoretical loss function that we had before. And, like, the parameters inside the neural network, if you look at this, like, L1 regularized model, it will actually, like, those parameters are exactly those that will implement Bellman-Ford. And then also, like, if you look at the performance of this, so that it's the second row here, if you look at the performance of this L1 regularized model across like many different types of graphs that are like way outside of the training distribution, you can see that like the loss stays quite low. The error stays quite low. Okay. So in summary, we have that GNNs will learn Bellman-Ford as long as they reach a low enough like sparsely regularized loss. And because they implement Bellman-Ford, they will naturally size generalize. And then empirically, we show that actually they can indeed learn these parameters which implement Bellman-Ford through just gradient descent and like an L1 regularizer. Yeah.
So in the previous slides, you were comparing to like other, there's like graph neural net.
Yeah. So, okay. So, yeah, I should explain this a little better. So, in this slide, we're comparing against like the neural network trained without any regularization, as well as like this standard graph neural network architecture, and this is the graph attention network. But you can just think of it as another message passing network, but like using a sum aggregator.
So can I think about like the gains that like your method has as like coming from the fact that the graph neural network you're using is very tailored to the problem?
Yes, exactly. Yeah. So we can have this because like yeah, the network is literally like implementing Bellman-Ford, and it's because of like this alignment with Bellman-Ford and also this sparsity regularization. Yeah. Okay, any other questions? Okay, great. Okay, so let me also switch gears a little bit and describe how like this algorithmic alignment idea can help us in designing networks that can solve hard shape fitting problems over point clouds now. Okay. And also before I get into this, let me also give you a brief primer on the sort of point cloud architectures that we're thinking about and like using neural networks to solve problems over point clouds or point sets. Okay. So if you're just given like a point cloud like x1 through xn, and you're asked to like come up with some network architecture that is going to like allow you to learn some label on this thing, like for instance, like if I want to build a classifier to say like, okay, this point cloud is actually from a bunny, or this point cloud is from like a teapot, something like this. One thing that you might do is like, okay, I have this great multi-layer perceptron model. I've used it before. It works great. Maybe I should just like stick all of my points together in like some huge matrix and then shove them through an MLP, okay? And then give me the label that way. I guess the issue here is that if I permute the order of my points, I'm not like, although the point cloud representation itself is like the same, and I want to get the same result no matter like what the order of points I have is, it's possible that like doing it this way is going to give me a different answer. This is not really what we want, right? Instead, we want an architecture that can naturally deal with like the permutations of the point cloud without actually changing the output. This is a property that people know as like permutation invariance, okay? And one of like the most basic and popular ways to do this is just produce some like high dimensional representation of each point in your point cloud, okay, through like some MLP, like this is all the same MLP, and then aggregate it in some way. And then after I produce like a global representation of my point cloud through this aggregation, I put it through a second MLP, and then I come out with my like desired answer or label or something. In practice, like two of the like most popular like basic architectures that people use for this kind of data is point met and deep sets. So you can see like they just differ in this aggregation. And people have shown that there's pretty good performance on many tasks, including like image segmentation, object classification, these sort of tasks. I wanted to highlight deep sets in particular because it has some nice theoretical properties that will also become relevant very soon. So given a multiset, a deep set can approximate any continuous multiset function, okay? The only issue is this, and it does that by like mapping every point to like a higher dimensional representation and then aggregating using a sum, and then finally like you have a final MLP that operates on this final global representation. The issue is, so you can see like what should the embedding dimension be for this inner like MLP, for this inner like V function, okay? It turns out that to represent like any, or to universally approximate any continuous multiset function, the embedding dimension scales with the size of the input point cloud, okay? So this is not super desirable because we're often like working practically with like large input point clouds, obviously up to millions of points. So we don't really want to scale the size of our neural network with the size of our like input data, right? Okay. And then, but there may be like special problems where you can solve them without needing this sort of scaling, okay? And indeed, in our recent paper from NeurIPS, published at NeurIPS this year, we demonstrate that like if you align a model with like a certain like algorithm, which is like very commonly used in computational geometry, we can actually solve like a family of shape-fitting problems without needing to scale the number of parameters in our neural network. Okay, with the size of the input point cloud. Okay. Okay, so let me also like give you the setting here. So our input is going to be some set of points, okay, in some d-dimensional space. And we also have some target shape that we're looking for. Like maybe I want to fit like a ball to it or an ellipsoid or a spherical shell. Okay. And then my output is going to be the optimal shape that covers my my initial set of points. So maybe this is like a minimum enclosing ball or like a minimum enclosing, like minimum width spherical shell. Okay. Our goal is to come up with an efficient neural network model that can solve these problems without needing to scale the number of parameters with the size of the input point cloud. Okay? So we really want our model to be able to work for inputs of different sizes. Okay. So I guess like why are we doing this? Well, there's always like, of course, we always want to be able to understand like what's the family of problems that we can solve without needing this scaling. And we are also looking for like a faster approximation of these sort of shape-fitting problems. And an added benefit is that we have like a differentiable way to solve these problems, and it can be incorporated maybe into some downstream ML pipeline. Okay. Okay. Right. So we want a general like neural network framework that can solve some shape-fitting problem. I'm going to use this encode, process, decode framework. Okay, it's very general. So what I'm going to do is I have some input point set. I'm going to encode it into some higher dimensional space. Maybe I have a processor network, like it does something, and then I'm going to decode back to some like the output, which is exactly like giving me the optimal shape covering that I want. Okay, and this decoder can maybe, let's have it be a deep set, okay, or something like that nature, because we know that it can universally approximate any continuous multi-set function. Okay. So so this will be the general framework that we use for solving these sort of shape-fitting problems. And now, like, I guess the thing to think about is how can we design like either this encoder, processor, decoder network so that we don't need to scale the number of parameters in our neural network depending on the size of the input point cloud. Okay, and so we're going to go to some ideas from computational geometry, like how do people in computational geometry like efficiently solve these sort of shape-fitting problems. And like one very common solution is to try to use something called a core set, okay? So a core set is just like a smaller fixed-sized subset of my original point cloud that I can use to approximate the desired quantity well, okay? So in general, like we start with some input point cloud P, okay? And then we're going to compute a core set Q, maybe these red circle points here. And then we can use our like some exact algorithm on Q to compute like my desired quantity. Okay, so that's how these sort of this sort of technique generally works in computational geometry. Okay, so then the question is like, what core set do people typically use? Okay, one super common one is called the epsilon kernel. Okay, so the epsilon kernel is just some subset of points that approximates like the width of your original point cloud. Okay, what do I mean by width? I just mean like if you look at this 2D representation here, the width is just like the extent. The width of a point cloud with respect to some direction is just like the extent of this point cloud, like from here to here. Okay. Yeah. So in general, like people use this epsilon kernel to approximate solutions to like what is called like an extent measure task. You can just think about it as like the shape fitting problems we're interested in. So things like the minimum enclosing ball, or like, you know, the minimum enclosing ellipse, or the diameter, something like this, right? And these epsilon kernels can be directly used as core sets for what's called a faithful extent measure, okay? There's a really nice survey. I guess I forgot to put like the information for the survey here, but there's a really nice survey for like these sort of epsilon kernel techniques from Pankaj Agarwal and Cyril Harpellet. So if you're interested, I encourage you to go to the survey. It's actually very nice. So one simple way that you can actually compute these epsilon kernels is to just like take some set of directions, okay? And then for each direction, I'm going to project each point, okay, onto that direction, and then take like the like point which achieves like the maximum maximum projection in that direction. So like if I have some direction U here, okay, I'm going to project each point down onto U, and then this point here will probably like give you the maximum, right? And then this is the point I'm going to take for my epsilon kernel. Okay. And okay. In like this, the number of directions you need to take does like depend on the dimension. It's the set of directions is like a people call it an epsilon or a delta net, okay, for like a sphere. But yeah, I won't bore you with the details. All you have to know is that you can have it so that the number of directions that you take and the size of your epsilon kernel is independent of your input point cloud, and it only really depends on the dimension of the points. Okay. Okay, so let's get back to this shape-fitting network. Like, how are we going to use an epsilon kernel? Like, how is that going to come into our neural model here? So the idea is like, if we have this processor network output an epsilon kernel, okay, then like the set of points which needs to go into the decoder to actually like approximate my solution is now like some subset of my input point cloud that's like, for the size of the subset, is independent of my original input. And so it kind of doesn't matter like how many parameters I need to approximate like the solutions from this decoder, right? As long as I can output an epsilon kernel from the processor, okay? So then like, you can imagine like, as long as we have this processor network simulate like an outputting like an epsilon kernel with bounded model complexity, then we have like a huge family of shape-fitting problems that can be solved without needing to scale the number of parameters based on the size of your input. Okay, so what we want is some neural model which implements the epsilon kernel. The challenge is that like okay, so if we think back to like the algorithm, right, for getting an actual epsilon kernel, we needed to use an argmax, right? This is a little difficult to implement with neural networks. So usually people will use like a softmax, right, as a differentiable form of argmax. But if we use a softmax, the resulting like subset that we get out is the resulting like set that we get out for Q is no longer a subset of P, okay? So that's okay. We just need to we need to just relax our definition of an epsilon kernel a little bit and use this relaxed epsilon kernel, okay? So now, instead of requiring that Q is a strict subset of P, we have that Q is a subset of the convex hull of P, okay? But it retains all the same properties as the regular epsilon kernel. So you can still approximate like solutions to shape-fitting problems using this relaxed version of an epsilon kernel. Okay, so now we kind of adjust our goal and we ask for a neural model which can output a relaxed epsilon kernel, okay? So we want some model which, given some sequence of input points, can output another smaller sequence of output points, okay? So we're gonna naturally go to maybe like a sequence-to-sequence model, okay? So you may think of like, naturally, maybe we can use a transformer to do this. So like really quickly, so a transformer is like a sequence-to-sequence model where you compute attention between all pairs of like points in your input sequence. And it's like quadratic time for forward pass. There are some more efficient versions of transformers or like models, like sequence-to-sequence models, which are sort of inspired by transformers, but don't require this quadratic time for forward pass. And the one that we're going to think about is the so-called Sumformer, okay? So the idea of the Sumformer is like, for each point, we first compute some global representation of our point cloud using this sum, right? So that's this term here. And then we compute a representation for each point by taking a function which takes in like the point itself and then also the global representation, okay? And this is linear time for forward pass. So it's more efficient, right? Okay, so it turns out that actually this Sumformer can really implement a relaxed epsilon kernel with bounded model complexity. You can show that a Sumformer can like kind of simulate an algorithm to compute like a relaxed epsilon kernel. And so, and in fact, you can do this with just one Sumformer block, okay? And so now that we know like a Sumformer can output a relaxed epsilon kernel with bounded number of parameters, we have that entire pipeline that we're thinking of can approximate solutions to shape-fitting problems with a bounded number of parameters. Okay, so yeah, again, like I guess these results, maybe they feel a little unsatisfying because it's just arguing about the capacity of your neural network. It doesn't really say anything about like, okay, does it actually bring me any benefit empirically? Does it, does this Sumformer actually work better as compared to the transformer? It seems a little, I mean, right now we use the transformer for everything, so it seems a little unbelievable. But yeah, let's look at a couple of experimental results, okay? So first, let's look at like actually outputting relaxed epsilon kernels using like a Sumformer versus a transformer, okay? And so so all of my test sets and train sets are going to be like point clouds in some three-dimensional space. And indeed, I see that this Sumformer based models, this S here, actually really does have like much better both in distribution performance as compared to like a transformer based model, and it also has much better like out of distribution generalization. Okay. Okay, so this is just for like approximating this relaxed epsilon kernel, right? We can also look at actually like using that entire framework that I was talking about to approximate solutions to like shape-fitting problems. Okay. So we test over 3 different types of shape-fitting problems. One is this minimum enclosing ball, another is a minimum enclosing ellipse, and finally we also test over this minimum enclosing annulus. Okay. And I also want to point out that in addition to comparing like this Sumformer implementation and the transformer implementation, we also test like 2 different training procedures. Okay. One is if we freeze like the processor, one is like if we explicitly train the processor on like on giving us a relaxed epsilon kernel and then freeze it. Okay. And then we only train the encoder, the decoder. And another one is if we train the entire model end to end. So here we're looking at like, okay, is outputting a epsilon kernel or is outputting a relaxed epsilon kernel really helping in this case? Okay. And yeah, it turns out that actually like we see like very good performance for like our frozen model across all 3 tasks. And then if we also look at this out of distribution size generalization problem or out of distribution generalization problem, we see that our frozen model also performs better. So here for each of the 3 shape-fitting tasks that we consider, we increase the input point cloud from like maybe 200 to around like 17,000 points per point cloud. And each of the models, I should add that each of the models are only trained on point clouds of size up to 200, okay? And you can see that actually like the Sumformer implementation, this like red highlighted line here, this y-axis is error. You can see that actually the error is like quite low, even as we increase the point cloud size. And then also, I guess this is a very visual problem, so let me also give you some visualizations. We can look at the actual shapes that are output by our like shape-fitting neural network. So this is like our frozen Sumformer model. You can see it's doing pretty well on like in distribution data. And then when we go to like out of distribution data, so many more points, and we also increase the size of the bounding box that we're sampling from, you can see that we also are getting pretty reasonable shapes out. Okay, yes?
Why is in the annulus problem? Does seem like the error goes up as this point cloud size.
Yeah. So yes, of course. So the error like does go up, yeah, as the point cloud size increases. I guess like the point is that still lower than the rest of them. Still lower. And then yeah, this annulus problem is like a more difficult problem also than like the other 2 problems because technically yeah. Yeah, the hole in the center makes it more difficult. Technically, you have to do when you use this epsilon kernel procedure to like solve this minimum enclosing annulus algorithmically, you have to go through an extra step called like linearization, okay? And in fact, that's why we have like this encoder part of the shape-fitting model, because like we hope that like the encoder can actually learn to do this linearization as well. So yeah, I think you don't see like quite as good generalization, I think, because like this is like a slightly harder problem and perhaps like the network hasn't fully learned to do the linearization well enough. Okay, yeah.
So I just have a couple of questions to make sure I understand the data set. So we're just doing like 1 point cloud and the set, like what is the like actual size of our data for?
Yeah. So we're training on like a whole like collection of point clouds.
Yeah. How many? Yeah.
Yeah. So we train on a set of like maybe 3,000 point clouds, and each of the point clouds have 200 points.
Because the reason I ask is I was just curious if this Sumformer is overcoming a lot of like the limitations we do see with the transformers, like this need for more data, I mean, did you get a sense of a better performance on sparser data sets as well? I was just wondering.
Can you repeat that question for the Zoom?
Oh, okay. So, sorry, I didn't
summarize the question.
Yeah, so I was just wondering whether we see gains in the Sumformer as well in terms of the size of data required. Like
Okay.
with our transformers, they're going to be greedy.
Uh-huh.
They're going to want more data.
Oh,
I
yeah.
was just wondering if you saw any gains in, you know, having
Yeah.
sparse data.
Yeah. Okay, so the question is like maybe the data set that we train on is like the transformer just simply requires more data. Yeah, that can definitely be possible. It's possible that the transformer just needed more data to train on in general. I think this may be also another advantage of the Sumformer. It's like a much more constrained model, and although like it's less sort of expressive than the transformer, like this can also be good in these cases where like you're learning these sort of in our case specifically for these shape-fitting problems, but maybe for like a more constrained problem or a simpler problem, actually you see some benefits from using the Sumformer. That would be like a nice, I guess, nice ablation to do is to like look at what happens.
And then
Yeah.
it's like, I'm sure you probably addressed it in your paper, but you have to really make sure that these two models have like the same size parameters.
Yeah.
And it has to be pretty consistent to be able to compare it like this.
Yeah. So yeah, we made sure like the size of the models were approximately the same between like these two derivations. Okay. And then finally I just want to say one last thing. We also tested our Sumformer model, like actually all the neural models, like the time it requires to actually compute a solution against like a classical algorithm, like the exact algorithm, and also using like the epsilon kernel plus the exact algorithm. And we found that, okay, actually these neural networks are, the time that they require is like much smaller, especially in the case of this difficult minimum enclosing annulus problem. Okay, so just let me summarize. So using this like epsilon kernel technique, using this epsilon kernel algorithm, we show that you can approximate solutions to a whole variety of shape-fitting problems with bounded model complexity. And indeed, using a Sumformer, and indeed it shows like better out-of-distribution generalization than its transformer counterparts. And the neural models are also more efficient in terms of like inference time than the algorithmic approaches. Okay, so let me just gesture also at some future work. So yeah, I want to continue to work on this direction, like when and under what conditions a neural network will learn some general like procedure or some like, or when will they learn algorithms? When can they learn something that is actually going to generalize for a much larger size input than what we see at training time? There are several like specific, like more specific directions that I'm very interested in. One is like kind of, I guess, like more on the empirical side is like right now we have we sort of design each model purposefully for like the shape-fitting problems, and we think of each thing individually, but it would be great if we could just have a whole benchmark of geometric problems and models where we could like quickly reference, like quickly test things. That's one thing. The second thing is I've been thinking recently about using like primal dual optimization methods. And it turns out that there's some interesting like convex optimization problems on graphs that like seem to match well with this message passing paradigm. So that's one thing I'm very interested in. And the third thing is like a little more like I haven't gotten very much into it, but I'm very interested in it, is like this distillation idea. I guess people have really been using it for like large language models and transformers, but recently there's also been some interest in like understanding distillation for graph neural networks, or like distilling to or from like algorithmically aligned models. This is another question that I'm like very interested in like looking into. In the long term, of course, like we want to be able to extend this from just like simple algorithmic tasks to actually like understanding if neural networks can learn solutions to like hard problems, like NP hard problems. There's already been like quite a bit of empirical research on like using GNNs or transformers to solve like combinatorial problems like the traveling salesman problem or yeah, like other NP hard problems. But yeah, this is a sort of long-term goal that I have. And then secondly, I'm also very interested in like applications of geometric deep learning, specifically for geospatial analysis. So previously I had some work on like using graph neural networks to approximate shortest paths on like large scale terrains. But I'd be very interested in sort of extending this work further and looking at how we can leverage like ideas from geometric deep learning to like downstream tasks like flood risk analysis or disaster modeling. And as you can imagine, size generalization is also super important for these sort of problems because oftentimes like you cannot directly train a neural network on like the scale of data that you're going to actually that these models will actually encounter at deployment time. So this is also super important for this. But anyways, thank you very much for your attention. I'm happy to take any questions now or offline.
Great. Thank you. So we're close to time, so we can, if there's a pressing question, maybe we can take one question either in the room or on the Zoom. If not, or if there are more questions than that, we will have Sam in cookie break at 3:30 in Milstein 514 in the 5th floor here in the Milstein Center. If you're on Zoom and have a Columbia or Barnard ID, you can get in with that. So that's another place for conversation and cookies. And seeing no pressing questions, let's thank Sam again. Thank you so much.